So let's resume our preliminary discussions of derivatives. So last time we saw that if at all the linear transformation involved in the definition of a derivative exists, it's unique. So we can talk about the derivative of f at x naught. Now, a couple of remarks. We have already seen that the derivative is unique. Next thing is that something familiar from one variable calculus. If f is differentiable then f is continuous at x naught. And the proof of this is the same as the one variable proof. So what do we do? Well, f of x naught plus h minus, we have this equation, f of given epsilon greater than 0, there exists delta greater than 0 such that f of x naught plus h minus f of x naught minus, now I'll use the derivative notation of Rudin, f prime x naught of acting on h less than epsilon h norm h for all h with norm h less than delta. And now it's just a matter of taking limits on both sides. So take limits. H goes to 0 on both sides. Then what one gets is, so I'll take the limit inside the norm sign. So that is one small thing one has to check. I mean, that's, you would have seen it in some form or another, but that has to be remarked upon. So what I'll get is limit as h goes to 0 of this left hand side in this stuff here. Outside the norm sign, I can take it inside the norm sign, limit h going to 0 minus f of x naught minus limit h going to 0 f prime x naught h less than or equal to epsilon times norm h. If you want to be very precise, you can even avoid this limit notation at this stage. We have already have this inequality for norm h less than delta. Then you just want to estimate f of x naught plus h minus f of x naught. Well, this will again start with f of x naught minus a plus h minus f of x naught, use triangle inequality by adding and subtracting f prime x naught h, and then you can end up with the same conclusion as I'm going to here. Here I'm being somewhat loose, but what I'm writing is correct anyway. So I'll after taking limits, so this f prime x naught h, this is linear transformation acting on h, so this as h goes to 0, this is 0, this is also 0, and finally I end up with limit h going to 0. This thing here is 0, which is what we wanted. So as a remark, let me mention that something which we'll use again and again. If f is any function from an open set, as usual, open set to Rm, x naught in U, then limit x going to x naught norm of f of x is the same as norm of limit f of x going to x naught. This is one thing. The other thing is that linear transformations are continuous. If T is a linear transformation from Rn to Rm, then T is continuous, i.e. limit x going to x naught T of x is equal to T of x naught. So I leave it as homework for you to check these. Apart from the exercises from Rudin, I'll be giving, as I've been doing so far actually, I'll be giving various unproved statements from lectures as homeworks. Now, there's something else, right? So this is this, right. In the other overall remarks about derivatives, if f is differentiable on u, this means at every point of u, then the derivative of f is a function from u. Now at every point of u, I'm going to get a linear transformation, namely the derivative. So that is, we have a notation for that, Rn to Rm. This will be important, this viewpoint, that the derivative in higher dimensions is a function from the domain of the original function, but the target now becomes the vector space consisting of linear transformations. Okay, so that's that, and then finally an example of a differentiable function. So let f itself be a linear function. F of x equals ax. A is an m cross n matrix. We know that every linear transformation from Rn to Rm can be written like this. So we take this. And so as in the real, as in the one variable case, a linear function in one variables is just something of the form f of x equal to cx, where c is a constant. And we know that the derivative is just c. The same thing happens here. For any x naught and Rn, f prime x naught is just the matrix A. Well, to be more precise, f prime x naught acting on V is AB. In other words, it's the same as f of V. And this is immediate from the definition. So by the way, this is the only way one can check whether something is the derivative or not, is you have to go back to the definition. So the definition is that we would like f of x naught plus h minus f of x naught minus f prime x naught h by norm h. And since I'm told that f of x equals ax, this is ax naught plus h minus ax naught. And here's the point that I already need, as I told you earlier, I need to know what the derivative is, our expected, our guess for the derivative. And that was just a h. Oh, I should not, there's no need to use brackets for the second one. And this is actually 0 by linearity. So even before taking limits, one gets 0. So one is done. The other thing is that I've changed my notation slightly. Earlier, I would write, if t is a linear transformation, I would write t of x. With that convention, I would have had to write, instead of, since f prime x naught is a linear transformation, I would have had to write f prime x naught acting on h. So, but instead, I've dropped the brackets around h. I'm just writing it like this. And for some weird reason, that's a standard thing in linear algebra or functional analysis. Whenever you have a linear transformation, Instead of writing t of x, one just writes t followed by x. So, okay, now let me prove the chain rule. So the setup is, I have two functions. This is f and this is g. And I have a point in the domain. So strictly speaking, g need not be defined. Here I've taken the second function to be defined on all of Rn, but that's not needed. What I need is, I have to talk about derivatives of g, so I need g to be defined on an open set in Rn, but I also want to compose g with f, so that open set should contain the image of f. We just need g to be defined in an open set containing the image of f, f of capital U. With that setup, then so what I would, if f is differentiable at x naught and g is differentiable at y naught equal to f of x naught, then this composed function g composed with f is differentiable at x naught as well, and the derivative of this composition is just a composition of the corresponding linear transformations. So it is g prime at y naught composed with f prime at x naught. Or if you are thinking in terms of matrices, it's just the matrix product of the derivative of g and the derivative of f. So let's prove this. If you have seen the one variable case, if it's done carefully, sometimes there's a wrong way of doing that. It essentially involves multiplying and dividing by some common factor, but that has to be done carefully. So it is this proof is very similar to that, but it may look a bit different. But you should go back and check the one variable case and compare. So what, let's just for convenience, let's give this derivative names. Let A equals f prime x naught and B equals g prime y naught. A and B are, you can think of them as either linear transformations or matrices. So, and then let's define u of h equals f of x naught plus h minus f of x naught minus ah v of k equal to g of y naught plus k minus g of y naught minus bk. For all hk in a sufficiently small ball centered at 0. The point is that f is defined on an open set. So, and x naught is a point, so if x naught, f is defined on this open set U, x naught is a point inside this open set. Therefore, it contains a ball around x naught. So anything of the form x naught plus h, where h is sufficiently small, norm h is sufficiently small, will be in the domain of f. Likewise, g, y naught is in the domain of g is an open set, y naught is in the domain, and so if k is sufficiently small, oh, I should be a bit careful here. Here I said for all hk, I said in sufficiently small ball centered at 0. The word, that's not quite correct. H and k are in different spaces. It's not the same small ball. So I should say insufficiently centered at 0, but that 0 is two different zeros in Rn and Rm. The origin of Rn and origin of Rm. With these definitions, norm UH, since f is differentiable at 0 at x naught, norm UH divided by norm H will go to, I'll write it as norm UH divided by norm H goes to 0, and this epsilon H is by definition norm UH by norm H. Vk equal to eta k norm k, where epsilon H goes 0 as h goes to 0, eta k goes to 0 as k goes to 0. So if this equation is, these two equations are confusing, just keep in mind that we are defining epsilon h and eta k by these two equations. And the point is that, so in other words, epsilon h is norm UH by norm H, eta k is norm Vk by norm k. The main point is that these two go to 0 as k goes to 0. Okay, so well, I'm also going to define, so now this K, this is the point where things become a bit, can become a bit imprecise if one is not careful enough. So here what I do is, this K which occurs in the derivative of the second function G, I want to choose it as a function of h. So I'll call it, let alpha of h f of x naught plus h minus f of x naught. So this alpha of h is what is going to serve my role as a role of k. And in fact, this choice is going to give me the desired equation. So now let's start finally writing down the main expression, f of x naught plus h minus f of x naught minus BAH. So by definition, this is g of f of x naught plus h minus g of f of x naught minus BAH. Here, I'll use this definition of alpha of h. F of x naught plus h I'll write as g of f of x naught plus alpha of h. Yeah, in fact, I might as well use the y naught notation. So this is y naught, g of y naught minus BAH. Remember that the goal is to prove that this entire thing, whatever I started with in this page, is less than epsilon times norm h. So let's see how to do this. Okay, now yeah, well, I just used the, so this is, I know that after all, this g is differentiable at y naught. And I have already introduced some notation for the difference. So let's go back here. This v business. So v of k is supposed to be this. So here instead of k, I'm using alpha of. So I'll just write it as v of alpha of h plus b alpha h. And I still have this thing here, BAH. All right, so then in fact I can combine these. V of alpha of h plus b times b alpha of h minus ah. what was, let's look at this. Alpha of h, yeah, alpha of h was this. If I do alpha of h minus ah, I just end up getting this UH here, this stuff here. Oops. So this is just what I called UH. Oh, well, not quite. Alpha of H minus A UH. Now I'll use triangle inequality and write it as V of alpha of H plus, now I'll use the norm of B alpha, B times UH. I'll use the operator norm property, operator norm of B less than or equal to this times norm UH. So this is operator norm of this linear transformation or matrix. Finally, divide both sides by norm H. As I said, I want to say that the entire thing is less than epsilon times norm H, or better still, divide by norm H on both sides and then say that as H goes to 0, I should get 0. So LHS divided by norm H less than or equal to norm B, that's coming from the second term, UH divided by norm H, which we had called epsilon H, plus what the other term was V of alpha H divided by norm H. Now, V of alpha H, again I just use the V of alpha H is I just use the definition of the V of alpha, this eta less than alpha H times eta of alpha H. Well, I still have to divide by, no, I've already divided by norm H, so that's, no, sorry, I do have to divide by norm H. Norm B epsilon H, I keep this as it is, and norm of alpha H is, again it's the same old thing. Alpha of H was norm, again I use the operator norm. See, remember alpha H was what f of x naught plus H minus f of x naught. So norm of this, so here I'm taking the norm of this. So the norm of this would be, and this thing is what I had called U of H plus AH. So the norm of this would be less than or equal to norm UH plus operator norm of A times norm H. So this would be, and when you divide both sides by norm H, this would be less than or norm H, and this would go away, and this would be, well, I had given it some name, epsilon H plus norm A. So that's what I'll use here. So actually I'm using the norm H on this part, norm H, epsilon H, and then eta of alpha of H. Finally we are done. So we can let H go to 0. I know that epsilon H goes to 0 as H goes to 0. So this goes to 0, and the norm A plus epsilon H doesn't go to 0, it just goes to norm A, but then there is this eta here, eta of alpha of H. As H goes to 0, alpha H will also go to 0. Alpha H is this thing here by continuity of F, and therefore eta will also go to 0. So this thing will also go to 0. So the whole thing will go to 0. So that completes the proof of. So it looks a bit confusing. So I suggest you, just as I said, do the one variable thing carefully first. It will be very similar to this. So let's stop here.